Hello viewers and welcome to another episode of Space Science with Python. Today we will create our first machine learning algorithm to classify between two different asteroid spectra. I know from last time we know that there are several classes, especially if you consider the bus classification that consists of over 15 or 16 classes. We have the main group class with the C, S, X and the other group. But today, in our very first video about machine learning algorithms, we will use we will distinguish between X-class asteroids and let's call it non-X asteroids. So yeah, we will try to build a classifier that tries to distinguish between the X classes and everything else. And for this video, we will work with a rather interesting algorithm called support vector machines. So we will not work with neural networks yet. I want to show you that also quite simple algorithms can also be used, or let's say not simple, but non-neural network machine learning algorithms can be used that have also a very remarkable performance. So it's not always needed to create some overkill neural network. Sometimes the simple algorithms are also quite sufficient. So again, the link is provided here to the GitHub repository of today's script. So it's script number 5 in the folder asteroid spectra. You simply have to click on open in Colab to open this script in Colab, and then you can run through it, assuming of course that you have already the level 2 data and so on that we created in our last previous steps. Now, the very first 3 cells are about importing the libraries. We open our Google Drive and read in the asteroid data here in the 3rd cell. So just as a quick reminder, let's copy paste the asteroids df. And what we have is the name of the asteroid, the bus classification, the main group classification, and we have per row or per asteroid a data frame that contains the reflectance spectrum. So the wavelength and the reflectance spectra normalized at 550 nanometers. Now, before we start diving into these machine learning algorithm, let's have a look at the algorithm called support vector machine itself. And for this, I would like to use my iPad and draw some examples how support vector machines look like or how they work. So of course you have to imagine this a little bit in a multi-dimensional space. It's a little bit difficult, but let's stick with 2 dimensions. And we will talking about 2 classes, so we will distinguish between X classes and non-X classes today. Now let's assume that we have one class that is let's call it a red class, let's call it the positive class, simply a red cross. And then we have another class, a negative one or a minus in blue. So this is just a small legend. And well, some of our data maybe lie here. So we have here a class, here a data point, here a data point. So in 2-dimensional space. Oh, I wanted to make a plus, but that's still a minus. So we have here like 5 data points on the right side. And then we have on the left side, we have another class, as I showed here in the top left. We have the plus classes here. Let's also draw 5 classes. And the idea is to distinguish between the blue and the red class here. So we have to somehow find a classifier that helps us when we are adding a new data point. Let's say we have a data point that's here. We would like to know, where does it belong? Does it belong to the red group or to the blue group? Now you will say, okay, this is a very obvious case, but the point is, well, what if it's more close in the middle or somewhere on the top or so? So we have to find a classification border between these 2 groups. And of course one could say, okay, let's draw a border. We draw it like this. And we separated our groups, plus and minus. So if we put a new data point here, it would be classified as a -1. But of course, you see the distance to the red group is way shorter, so it wouldn't make sense to classify it as a blue one. So the idea of the support vector machine is to find a separation or a classifier margin or a plane that maximizes the distance between both classes. So in our case, it searches in an iterative way. It's a optimization algorithm, a plane that maximizes the distance between the points here. Okay, it should be equidistant, but yeah, you get the idea. So this is about how the support vector machine tries to find it. Maybe I will create a concept video about support vector machines in detail, where I will also explain the mathematical background of this. But this is more or less, let's say, the way support vector machines work. Now, of course, there are some things one has to consider, because the data points never look that perfect. So let's take another example. Let's draw again some pluses and also some minus classes here. And maybe we have an outlier of the blue class here between the red ones. So drawing a straight line would be difficult, or not possible at all. But of course, you see with your naked eye that, well, a line would maybe look like this. And for these cases, there are also some methods to punish certain values, so that you add some kind of penalty value that ignores these data points that lie in between or close to the other group. Another case is also if you, for example, let's create some red classes. If you have here some dots and we have our other classes embedded. Also here, you cannot really define a line or something or the plane to distinguish between these data points. But what you could do is you could apply some kind of function to increase, let's say, the dimensionality of the points. So for example, imagine you transform this graph now in 3D space, where these points are on some kind of summit and the other points lie on the ground, and then you can draw a line or a plane in between. This can also be applied to create a data set that is linearly separable. Well, and this is how the support vector machines, well, in a very conceptual way, look like and how they work. Again, the mathematical background, I will provide it in another video, but this is the most important thing you have to know for today's session. So back to our script to prepare everything for our support vector machine classifier. First of all, we have to do some data preparation. I know we have our level 3 data, but for our algorithm, we still need to do something. One thing is that we would like to distinguish between the X and the non-X classes. And for this case, we will define a new column temporarily only for this video, for this script. So it won't be stored anywhere, where we say, okay, we take the main group classification, main group, and we apply a lambda function. And we say that the class is 1 if the main group equals 2x. Now, I need 2 equal signs. Otherwise, it's 0. So this is now our new column we will create. And now we need also to extract our spectra and put them into some NumPy arrays, also as well as the new classification, column. So what we do, we will create a NumPy array where we say, okay, we would like to take the reflectance spectra, and I think it was called norm at 550 nanometers. So this will be converted to a list for K in asteroids spectrum df. So remember, spectrum df, this column contains a lot of data frames. So this is what we need to do to extract the spectra. And then we need, of course, also the labels itself. And it's also a NumPy array where we say we take the class, so that we defined just in a moment ago, also to list, and then we convert it. And just have a quick look. We have the asteroids spectra now in a NumPy array. So each row is now a spectrum, and the corresponding classes are here. Yeah, okay, sorry, everything is 0, but let's take a look at the sum. So summing up every number 1, and we have 240 classes. And yeah, the total length is, I think, 1,100 or so. So our spectrum has, like, I think each spectrum has 49 features, so 49 steps between, I think, 440 and 700 something nanometers. And it's also important to mention the so-called curse of dimensionality. So if you have high dimensional data, you need more training samples so that your machine learning algorithm is sufficiently trained for unknown data. And there is a rule of thumb. So for example, if you take a look at Wikipedia or so, or other resources, they say that, yeah, you should have around 5 training examples per feature. So we have like 45 or 49 features. We have, and this times 5 would mean that we need per class around 250 data points, or 250 spectra. And well, for our, in total, we have like 1,300. So 1,100 are for the non-X class. And okay, we have a little bit too few spectra for the X class, but yeah, let's stick with what we have. Of course, we have always to create some kind of baseline to compare with some kind of algorithm, so to create some baseline, some naive classifier. But I will put this into the end of the video. So for now, let's just continue creating in a machine learning algorithm and see how things work. The next step would be to separate our data into training and test set. So even also the training data is then, yeah, has then a training part and a validation part. You train on this data, and then at the end you apply the test data. So the algorithm does not, let's say, see the test data. It's just being applied to verify or to check the performance of the classifier that is based on the training data. So you have always to split between the data set into a train and test data set, because you want to have, otherwise your algorithm would overfit on all the data it sees. So it's very important always to separate it. And to split our data, we have to use something from scikit-learn, and it's called the stratified shuffle split. There it is. Because the point is, the stratified shuffle split, strange word. I will just copy paste it. The point is, if we split in the test and the training data, we have to be aware that we would like to separate in such a way that the ratio of positive to negative classes remains the same. So we don't want to have something like a 50-50 weighting in the training and then, I don't know, 5%, 95% in the test data. That would cause a severe bias, and at the end of the day, it wouldn't say anything about our algorithm. Also, if you're training some algorithms, you have to split the data several times. You can make some k-fold training, k-fold validation, and so on. But here in our very first video, we will keep it very simple. We will not talk a lot about splitting data. We will just train an algorithm so that you get some idea how these things work. So we will split our data only once. And we will keep a test size of around 20%. So around 20% of the data are being used for testing purposes. Okay, so how does it look like? We say, okay, for train index and the test index, so we're creating indices for our data set. We use the stratified shuffle split dot split. And our input is the asteroids X and asteroids Y. So the argument with all the labels, it's quite important for the splitting algorithm. And now we can say, okay, we will create a training spectra and test spectra based on the asteroids data we just created, where we have the training index and the test index. So let me just copy paste it here. The test index, and the same things apply for the labels as well. So we have here the Y training, the Y test, training and test. Now this looks good. Let's run it. And I got, it's called not nsplit, it's nsplits. So there's the error. No error spawned. Perfect. And now we should maybe check, whether the ratio is still the same. So let's say the sum. So let's print it. First, we print the number of training labels, so the number of all positive training labels divided by the length of the training labels. It's like, okay, 17 or around 18% are X-class asteroids. And if we take now the testing array we see okay, that's strange. Let me just check. Yeah, I did a mistake here. There should be Y, not X. So I have to rerun the splitting. And we see here also 18% belong to the testing array. So the ratio of our imbalanced data set is preserved. And this leads us now to another wording, the imbalanced data set. So if we are talking about the baseline, like flipping a coin. So you want to create a machine learning algorithm that computes or predicts a coin flip. Okay, this is maybe a rather useless example because a coin flip is always random, but let's assume we have some kind of magic coin where we can perform some kind of prediction. Then let's say whether it's head or tails, it's 50-50. So the baseline is 50%. So we have to we have to create a prediction performance of more than 50% to beat, let's say, this random classifier. For our imbalanced data set, we've also take care how to do it here. We will take a look at this later, but to support or to let the machine learning algorithm know that our data set is imbalanced, we have to provide something called something like a class weighting. And for this we say it's 1 divided by the sum of Y training divided by the length of the training. So it's simply the inverse of the 18% as an integer rounded up. So it should be something like around 4 of up. Here it's Now 0, it should be 5 actually. We have the sum of the Y training. Let's take me a quick look here. It's 190. And the length, 1000. Yeah, maybe I'd have to take it as a float, otherwise it won't work. Or maybe I should simply, no, not a float. It's Python 3, it shouldn't matter. I forgot some brackets. I think this is more important. Yeah, so we have now a weighting of 5 for our positive class, and this is something we will need also in a moment for our training. Okay, now in our next step, we can we have to scale our data. Now, you know, maybe from the neural networks, if you have worked with the MNIST data, for example, the data are scaled between 0 and 255 or 0 and 1. And some other algorithms require some other scaling. So it's never a good idea to put just the naive data into some machine learning algorithm. So for example, let's take an example. You have some algorithm that considers the temperature, but which varies maybe between 0 degrees Celsius and 100. And you're also considering the atmospheric pressure in like millibar or so, which is then 2 orders of magnitudes higher. If you're not scaling it, your machine learning algorithm will, of course, overweight the larger numbers. So you have to scale them accordingly. Otherwise, it's it can get a little bit chaotic. And in our case, we are using something which is called pre-processing. Or not pre-processing. Pre-processing is the submodule in scikit-learn. We will scale our data. We will subtract the mean. We will subtract the data by the mean and then divide it by the standard deviation. So we first create a scalar which calls a pre-processing module and uses then the standard scalar. And then we fit our training data here. And then, of course, we have to scale our training data. So I call it xtrain scaled. And then we use the scalar and then simply transform it with the scalar we just defined. And the test data later, they also need to be scaled, but based on the scalar that is being defined based on the training data. So that's really important to not create a second scalar. The test data is totally naive. It just uses the scalar from the training data, and it then uses also the machine learning algorithm based on the training of the data. So let's run it. And then we are good to go for our next step, namely the training. Okay, let's continue now with the training. And for this, we import the support vector machine submodule from scikit-learn. So from sklearn, we import the SVM, so the algorithm I explained in the beginning of the video. And we create a class, the classifier, where we call svm.svc. We use one of these. So for now, we will not optimize anything. We will not do fine tuning or find the best methods. We just use one of these functions one of these kernel functions that are being applied to our data. We will use also a punishing value. I just played around a little bit prior to this video to get some decent results. But in a future video, we will also see how to do this in a more automatic way and to create some kind of searching algorithm that finds the best kernel and also the best punishment values. But for now, in this video, we will stick with some very basic values. So just stay with me and let's apply the values we just write down here. So this is now our classifier, our support vector machine. It's now purely naive. It didn't see any data. It's just there, totally random initialized. And well, random initialized classifiers are quite worthless in our case. So we have to fit our data we have to fit our scaled data, and we have to provide it our labels. And this is what we can do now to, I have to do from. No, the way around. From scikit-learn, I have to import SVM, of course. Now this is very bad. Okay, you see the training was extremely fast. So we have now a classifier based on our spectra data that is now hopefully able to distinguish between different data sets, between different classes. And to check the performance, we have, of course, to apply our test data on it. So first we scale our test data with our scaler. So transform x test without creating too many typos. And then we can compute our prediction labels on the test data with our classifier class. So x test scaled. So this is all it takes to train our algorithm and to predict labels based on the test data set. So you see, you get the idea, right? That a lot of things in machine learning or data science are simply data pre-processing all the time. And then at the end of the day, it's just simply calling a single or two lines of code. Of course, the optimization algorithm behind these two lines is very sophisticated, of course. Here we are simply the consumers of this training algorithm. So super grateful that there are nice libraries like scikit-learn or Keras. The next step is the metrics. And the metrics to see, well, to check the performance of our algorithm. So we take a first look at the data. What can we do? We can, first of all, we will take a look at something which is called the confusion matrix. So yeah, let's import the confusion matrix from scikit-learn. I will explain you on the fly, hopefully, if I'm able to do multitasking, what this is all about. So first, let me just compute this confusion matrix. And the confusion matrix takes our expectation labels. So the labels from the test data that are the actual labels, yeah, the labels that our training algorithm has never seen before. Yeah, so for the training, we use the training. For the testing was only, yeah, the machine learning algorithm was only applied, or applied only the classifier applied this classification decision thing on our test data, and now we compare the expectation with what we predict. Yeah, we did it here in the previous cell, and we compute our confusion matrix. And this confusion matrix looks like this. Quite simple 2x2 matrix, and it's actually quite simple to understand. It also increases if we have more values. We have here on the diagonal our so-called true negative and true positive values. So the true negative says that 217 non-X classes have been classified correctly as non-X classes, and 45 X classes have been correctly identified as the X classes. Here on the top right, we have the number 4, and this indicates the so-called false positive. So, for example, a C class spectrum was classified as an X class spectrum, or an S class was classified as an X class. Yeah, so this is like wrong values from the other group that are being classified as an X class. And here we have the false negative, which means that 2 spectra from the X class have been wrongly classified. So they they haven't been found at all. Now there are a lot of other different cool metrics to consider if you want to determine the metric, the power of your machine learning algorithm. And this always depends on the use case. So if you think, okay, what are the best metrics? Well, it depends on your question. So for example, imagine you're working for a credit card company where you have to create a machine learning algorithm to detect credit card fraud, so a fraud detector. What are the metrics that are important? Would you like to find a lot of frauds, but with the risk that some non-frauds are classified as frauds, or the other way around? So let's say your consumers would be, they would be quite angry if their credit card would be an attack on the fraud and you wouldn't recognize it. The other way around, it would give them a feeling of security. So there are a lot of, you detect all the frauds, but also non-frauds. And in the case where your algorithm is not sure whether this is a fraud or not, there is some, the script or the software is asking the customer, hey, did you authorize this transaction, yes or no? So it's always quite important what's the use case. So let's say in our case, for example, this algorithm could be, let's say, a support tool. So the scientist wants to find all X classes. He definitely wants to have this number. The best case would be 0. But he doesn't mind if, for example, 40% are non-X classes. He just wants to see all X classes. Afterwards, he will select them by hand anyway. He just wants to reduce the huge amount of data with this tool. So you have to see, okay, I would like to reduce this number here. Maybe I get it down to 1 or even 0, and maybe this number here, the false positives are increasing to 15. The scientist maybe doesn't care because he wants to find all X classes. So again, this depends really on the use case. So there is no correct answer to this. But there are some other metrics that help you to determine the score of your algorithm. And the most important scores are the so-called the recall score, the precision score, and the F1 score. We'll get to this in a moment. I just want to show you that a nice article is being provided by Machine Learning Mastery about of all evaluation metrics for imbalance classifications. So I can highly recommend reading through this article. Go through it. This link is in the description. And we will also, in a future video, maybe in the second video from now on, we will also take a look in more detail into this metrics to distinguish between different algorithms we will compute. And also here, there's a nice graph that asks you, okay, what would you like to do? Class labeling or probabilities? And then it tells you what kind of scoring or metric is the best for your case. Now, what is the recall and the precision score? So let's compute the recall first. The recall is like the ratio of correctly classified X spectra, considering the false negatives. So the false negatives are the values that were displayed. False negative were displayed here. So this is false positive, this is false negative. So it gives you a feeling about your performance, and we can use scikit-learn metrics dot recall score, and then we say x test prediction, and then we round it to maybe 3 or so, and then we can print the score. So let's see. So this is now our recall score. So you see, it would be quite naive, of course, to consider all the values and then just divide it by 2 or so. We have to consider the imbalance between these values. And the precision score is something that considers also the false positives in our case. So it takes this number here, the true positives, and also the number 4 here. So the value we will compute for the precision is a little bit smaller in our case. So it should be like, yeah, if you take here 45 and 4, maybe 90% or so. So let's see what the precision says. Precision score. It should be like 90 or 89, 91 or 92%. So it's a little bit smaller, which correlates with the number, with the larger number here in our confusion matrix. And let's call it a combined score that takes both the recall and the precision into one metric is called the F1 score. You can, yeah, think about it a little bit as like the accuracy for imbalanced data sets, for imbalanced cases. And here we use also the metrics, and then we compute the F1 score. So it should be something in between, like, I don't know, 93% maybe or so. F1 score. Yeah. Again, we will go through these metrics a little bit more detail over time. So this is just their first impression for you how to compute it. So yeah, if we just would take this values here naively, sum everything up, and then dividing by, let's say, 45, it wouldn't say anything, right? Because our data set is imbalanced. For a problem where your classes have a distribution of 50%, 50%, it's of course more easier, right? If you have accuracy of 90% and your classes are equally distributed, it of course gives immediately a better understanding and feeling than imbalanced data set. For imbalanced data sets here, you need this recall score, you need the precision score, and also the F1 score. We could also think, okay, what is then, for example, the F1 score for a complete random classifier? So, as I said, for tossing a coin, accuracy of 50% is like, yeah, doesn't help us because 50% of flipping a coin is like, yeah, wild guessing. How does it look like in our case? Well, here, of course, we have still two classes, as the X and non-X class, but what I show you here can also be applied for any other multi-class cases. So we are asteroids, yeah. I don't know. We are taking our asteroids labels, or our original ones, everything. We create a copy, and then we are shuffling our new labels randomly. So we are shuffling it, let's say a classifier that's completely stupid. It's just shuffling it randomly. And now we compute the F1 score of our original labels and this shuffled labels and see what's the F1 score. What's the F1 score in our case here? So F1 score, let's call it random. We use also, again, function here, but now we use the prediction now is our randomized values and the original ones are here. So yeah, let's see what the F1 score is here. So again, we have our original labels. I shuffled them randomly, and now I compare the original label with some shuffling. Yeah, so the worst classifier, it's just like, again, a random shuffler, and see what's the F1 score here to see if we beat a simple, stupid algorithm that just randomly, yeah, throws numbers. And the F1 score for our random shuffler is like 20%. So yeah, we beat some kind of baseline. Of course, we can define also other baselines, and of course you have to define baselines before you train anything. But again, this is our very first video where we are talking about support vector machines, where we are not doing any fine-tuning or grid search or creating some pipelines. It's just for the sake of getting a feeling, an introduction into this amazing topic. I don't know if you will work with scikit-learn or so, I can highly recommend working with the scikit-learn package. So using neural networks is sometimes an overkill. So even for simple cases, these algorithms are also quite strong. You see here our F1 score of over 90% is quite feasible. And we didn't put a lot of thoughts into this, right? We just put some random numbers there and we have a really nice scoring. But remember also our spectra view from last time. With the naked eye, we already saw huge differences between the C class, the S class, the X class. So I already said last time that, I hope that we can create a naive classifier that is performing quite well. And I think we can be proud of our results today. Good. I hope you enjoyed the session. And again, the link is on GitHub. I wish you happy coding.